Okay, now let's look at a couple of questions. Okay, if x changes from 1.2 to 1.7, what's the change in y? Okay, well, let's look at the x cubed graph and answer this for the x cubed function. Okay, so let's see. Where's 1.2 on the x-axis and where's 1.7 on the x-axis? Close the lid. Okay. Well, 1.2, let's see, here's 1, here's 2. I subdivide that in half. I get 1.5. Now 1.2 is going to be between 1 and 1.5, a little closer to 1. So the halfway point would be there, so 1.2 is going to be about here, let's say. Not sure I did a really good job of that. I never can tell where the point of the chalk is going to be. But there's x equals 1.2. And 1.7 will be about the same distance to the right of 1.5. And that's going to occur about here. Well, let's see if we can figure out what the change is in y. If I project up to the graph and over, starting at the x equals 1.2 point, here I get the y value. When x equals 1.2. If I go to 1.7, go up here kind of carefully. Don't have a lot of confidence I'm going to get a good estimate here, but we'll see. Okay, here's the y value. For x equals 1.7. Just knocked my squeegee into my buckets. I've got a really wet squeegee. Kind of slipped it too. Water all over the floor. It's a tile floor, it's okay. Okay, as long as I don't slip on it, that'd be kind of entertaining. Okay, so again, here we have the value of y equals x cubed, or at least a point that we think approximately represents the value of y equals x cubed when x equals 1.2 and when x equals 1.4. The change in the y value well, the y value starts here and ends up here, so the change can be represented by this red arrow, pinkish red. I think they'd make a better red. So I'll label this the change in y on the interval . 1.2, 1.7. And now we can estimate how big that change is. Do that in one of two ways. I can subdivide things here. Okay, subdivide the interval from 0 to 8, subdivide it again, divide the intervals between, and get a scale. And I could then estimate this value and this value. Or I could just say, well, let's see. This arrow, if I do the length of that arrow here, and then the length here, and then the length here, about 3 of these arrows seem to make up 8, maybe a little less than 3. Well, 1/3 of 8 is 2 2/3, which is 2.66 repeating. A little less than that might be 2.5. Okay, so I'm going to just estimate the length of this to be 2.5. Again, I could estimate this coordinate, I could estimate this coordinate. I could probably find out, I'd probably come out with something different than my estimate for the length of this, because everything's approximate and I'm just doing the best I can with my eyeballs and, you know, my fingers and so forth. But I'm going to say the estimated change is 2.5. I'd fudge that a little lower, maybe 2.4. But there it is. Okay. I'll also comment that we get something out of this. We get a fundamental triangle between these 2 points. And we see that the run corresponding to that triangle is the length of this side, which goes from 1.2 to 1.7, and that is 0.5. And the rise is 2.5, so it looks like the slope of this thing is about 5. And I can use a little bit of what I know about calculus. And cube 1.4, I get about cube 1.4, I do 3x squared for 1.4. It gives me about 6. Okay, and I just figured out the actual slope of this graph when x is 1.4 is about 6. Matter of fact, yeah, very close to 6, a little less than 6, which goes with this estimated change. So that's just a little teaser. When you learn calculus, you see how I did that. But the one thing I want you to see is we got a fundamental triangle there. And we can do that geometrically. Okay, well, we're going to also do a short video where I answer. Well, actually, I'm going to go ahead and do this. If y changes from 1.5 to 0.7, what's the change in x? Well, let's see. Y equals 1.5 here. And y equals 0.7. About here. So if I go over to the graph and down here, well, an honest estimate is a little more than 1/2 when y equals 1.5. It's an honest estimate, it's not a very good estimate, I'm going to call that 0.6. And then come down here and maybe we have this. So we have maybe x equals 0.6 here, x equals 0.7, yeah, that's good, 1.1 here. This red arrow gives you the change in x corresponding to the change in y from 1.5 to 1.7. I could have estimated the length of this thing. I could take that red arrow and compare it here. It looks like my estimate would be 0.5 in that case too. There are two ways to do it. Over here I just estimated by looking at the length of the arrow compared to the interval from 0 to 8. Here I actually estimated x coordinates and took the difference. Either way works. And I'll comment that, you know, we have a fundamental triangle here. Now halfway between these points would be probably around x equals 0.8. Between 0.8 and 0.9 I'll go with 0.8. If I do the calculus, I evaluate -1 over x squared at 0.8, going to give me about 1.5. The run of this triangle is 0.5, the rise is 0.8. 0.8 divided by 0.5 is 0.6. Yeah, so now I'll probably ask some questions about these fundamental triangles because I didn't include that because we wanted to get the idea of making estimates from the graph. But we can do this. Okay, the bottom line you want to take away from this is if I have two x values, I can estimate the change in y. If I have two y values, I can estimate the change in x just by doing these projections. And then there's a fundamental triangle involved, and the legs of the fundamental triangle are the differences in the y and the differences in the x coordinates. So we get a slope automatically. And that slope relates to something really, 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 really important from calculus. We're not going to do the calculus of it. We're going to see how we interpret slopes a little bit later in the course.